Yes, welcome back, student. Today we are going to understand the next lab program from part B. That is the lab program number 13. The program is like this: write an embedded C program to interface an external DAC to generate square and triangular waveforms. So, in the previous session, you understood how to display an hello world message using the internal UART of LPC2148. Now today you're going to understand how to interface an external DAC to LPC2148 and generate a square and triangular waveform. Now what is a DAC? Digital to analog converter. You give the digital data which is in terms of zeros and ones. Now this DAC will convert it into an analog data. Now what analog data we get out of the digital data now is a square wave and a triangular wave. Now and again what we are using an external DAC. So we use an external 8-bit DAC, that is DAC 0808. That is what will be interfacing with LPC2148. Now before I explain the external DAC, interfacing external DAC to LPC2148 and generating square wave and triangular wave. Now first I'll focus on the internal DAC. So LPC214 has got an internal DAC as well. Now the internal DAC of LPC214 is a 10-bit DAC. Now already there is a built-in DAC present inside the LPC2148. So digital to analog converter is built into the LPC2148, and that is the 10-bit digital to analog converter. So the external DAC which we will be interfacing with the LPC2148 later is an 8-bit DAC. So first we'll understand how to generate the square and triangular waveform by using the internal DAC which is present inside the LPC2148, and later we'll understand how to interface an external DAC with LPC2148, that is an 8-bit DAC, and generate the square and triangular waveform. But lab experiment is interfacing an external DAC. First I'll explain how to interface how to use an internal DAC to generate the square and triangular wave. After understanding that, we will move to how to interface an external DAC to LPC2148. Now first this is what we are understanding: internal digital to analog converter, internal DAC. Now is most widely used to generate the analog signals. DAC is most widely used to generate the analog signals, for example sine wave, triangular wave, etc. Now we are not going to generate the sine wave now. Now we generate the triangular waveform and the triangular waveform and the square waveform from the digital data, the digital values. Now as already told, LPC2148 has got a built-in 10-bit DAC. So with resistor string architecture, it also works in power down mode. So it has an 10-bit DAC. That means the minimum data what you can give for this DAC is 0, and the maximum data what you can give for this DAC is 1023. Why 1023? Because 10-bit it is. If I write 10 ones, its value is 1024. Now the minimum value that you can give for this DAC is 0, and the maximum value that you can give for this 10-bit DAC is 1023. Later you'll understand that. Now LPC2148 has analog output pin AOUT on chip. So there is the analog output. In order to take out the analog output from LPC2148, there is an analog output pin which is, as I told, 64 pins are there in LPC2148. Now among the 64 pin, one pin is an analog output pin named as AOUT. Now what is that? This is the pin, the one which is marked in the red. You can see here P0.25. It is AOUT, analog output pin. This is the analog output pin which is available in LPC2148, and this analog output pin, internally it is connected to the 10-bit DAC which is present inside LPC2148. And if I want to take the analog output, I have to take from this P0.25, because this is the pin which is acting as an analog out, and this is the one which is connected to the 10-bit DAC which is built into this LPC2148. Now LPC2148 internal DAC pins Okay. Now A out, as already told, analog out. This analog out pin of LPC2148 DAC peripheral, where we can get analog output voltage from the digital value. As already mentioned, for the given digital value, you give the digital value to the 10-bit DAC which is present here, 10-bit data to the DAC which is present here, and this is the pin which will give you the corresponding analog output. So A out, and then it also has Vref, the reference voltage, because to the DAC which is found inside the DAC which is built present inside this LPC2148, you have to give the reference voltage. So the reference voltage pin number is the 63 Vref. You can observe here Vref. This applies all the voltage requirement of the DAC, internal DAC. And apart from that Vref, which is pin number 63, there is also VDDA and VSSA. So this is analog power and this is analog ground. Now what is the pin? Pin 7 is VDDA and pin 59 is VSSA, and again these two pins are connected to the DAC which is there inside the LPC2148. I'll show you here. Now pin number 7, pin number 7 is here. This is VDDA, analog power. So, and then one more VSSA. VSSA is pin number 59. So 59 is here, VSSA. This is again, this pin is connected to the DAC which is present inside this. This pin is connected, this pin is connected, this pin is connected, and VDDA is also connected. So these are the internal DAC pins. Now, what are internal DAC register? This register is very important. So the DAC which is found inside LPC2148 has a register called as DACR. Now what is DACR? DAC is DAC, digital to analog converter register. DAC register it is. Name itself is DAC register, DACR. And how many bit register it is? It is a 32-bit register, and it is again a read-write register. This particular register can be read also, and you can write this register also. And where is this register found? This register is found inside the internal DAC, 10-bit internal DAC, which is found inside the LPC2148. Now this is the format of the DAC register. 0 to 31, it's a 32-bit register, and 0 to 5 are reserved. That means, well, let us not worry about this part. And again 6 to 15 is a value. This is where you'll be giving your digital data. Now I want my digital data to convert it into the analog data. So your digital data should be present from the 6th bit of a DAC register to 15th bit of DAC register. So 6 to 15, how many bits are there? You can count 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So totally 10 bits. 6 to 15, you have 10 bits, hence it is called as a 10-bit DAC. And 16th is a bias, and again we don't focus on this much. 17 to 31 is again reserved, we don't focus on this again. Now our focus is only on the 6th bit to 15th bit of DACR register, because this is where your digital value will go. You have to give the digital value from the 6th bit to the 15th bit of DACR register, and from here this digital value which is present here gets converted into analog data, and that analog data you'll get out of P0.25 pin. P0.25 pin. Now that is what I've written. Bits 6 to 15. 6 to 15. That is the value. Here you're going to write the 10-bit digital value which will be converted into analog voltage. Now how this 10-bit digital value is going to convert into the analog voltage? This is the formula that is used. Now whatever the value you give here, say for example I make all the 6th bit till 15th bit as 111. Now binary 111, 6th bit till 15th bit, all the bits I'll make it as 1. 10 ones I have. Now what is its decimal equivalent? 1023. 1023 by 1024 into Vref voltage. The Vref voltage that is given here in pin 63. So using that it will compute, that is what is the analog output or the voltage. So this is the register. I hope you understood. You got to remember this position, 6th bit till 15th bit of DAC register is very important, because this is where you'll write the digital data that needs to be converted into analog data. Now, so internal DAC programming steps. So I want you understood. This is one important register that we use, and again in this register you got to remember it is from 6th bit till 15th bit. Your digital data should be in this position, 6th bit till 15th position. And another thing is, what is A out? A out is P0.25. This is what you have to remember. Next, now what are the steps involved in programming the internal DAC? So first thing is, as I already told, P0.25 is necessary because this is the one which is acting as an analog output pin and which is internally connected to the DAC. So now how to make this act as analog output? Now you have to make use of pin cell register for that purpose, because using pin cell register you can define 4 different functions for each of the port pin. Now since this 0.25 is in the range 0.16, port number 0.16 to 0.13, now which pin cell register I have to use? Pin cell 1. Now if the port pin is in the range 0.0 to 0.15, you have to use pin cell 0 register. Since it is in the range, because even in my earlier classes I have explained this, let me not spend much time on this. Since this P0.25 is in the range 0.16 to 0.31, I have to make use of pin cell 1. Now pin cell 1 I am assigning this 0, 0, 0, 3 zeros, 8 and 4 zeros. Now why this data only? Because now when I expand this in the binary, this 0, these 4 zeros corresponds to this 0, these 4 zeros corresponds to this 0, these 4 zeros corresponds to this 0, and this 1 0 0 corresponds to 8. This is 8 in binary, and this 0, these 4 zeros for this, these 4 zeros for this, these 4 zeros for this, and these 4 zeros for this. Now this is, I'm saying P0.25. In order to make this P0.25 function as analog output pin, now what are the data I have to give? 1 0. Now where I have to give? In the bit 19th bit of pin cell 1 and 18th bit of pin cell 0, they must be made as 1 0. Now that is the reason. You can count from here. This is 0th bit, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. This is 18th bit and this is 19th bit. So because 18th and the 19th bits are reserved for defining the function of P0.25. This you can refer in my earlier recorded videos or the PPTs. I have explained it clearly. Now this 18th bit and 19th bit are reserved for defining the function of P0.25, and again to define the function, analog output function for P0.25, the value must be 1 0. That is what bit 19th bit, this I'm making it as 1 and 18th bit is made as 0. When I make this and assign it to pin cell 1, now it will make P0.25 function as an analog output pin. Now after the moment you make P0.25 as act as an analog output pin, so next thing what you have to do is writing a 10-bit value which we want to convert to the analog form in the value field of DAC register. So next you go for writing the 10-bit value to the value field of DAC register. So then it will convert and will give the analog form of that digital input via pin 0.25. Next. Now DAC register, understanding more with respect to the DAC register. The value is a 10-bit field. This is a 10-bit field. DAC register used to give 10-bit digital input, that is 6th to 15th bit, that is equal total number of bits is 10 bits. Now the minimum value what you can give in binary I have written 10 zeros, that is nothing but in decimal 0, and the maximum value that you can give here is all 10 ones, and that is equal to 1023. Now what is that I need to do in order to generate the square wave? Now I have to give the value. Okay, so this is just have a look. I have written the square wave here. This is what the square wave is. So equal on and off time. This is on time and this is off time. This is on time and this is off time. Now give value 1023 in DAC register for 1023 times. Now what is that I'm doing now? I'm giving this value to the value field of DAC register. So this value field I'm giving 1023. To give 1023 here, Now I have to make 6th bit till 15th bit as 111. If I make all the bits from 6th to 15th bit as 111, so the value is what? 1023. That is what I'm doing. And then I'm running a loop. Count is equal to 0, count less than 1023, count plus plus, value is equal to 1023. DACR, this is the register. To that register, what I'm assigning is 1023 left shifted by 6 times. Now why? So this is what the value I'm assigning to the value. Value is a variable here. 1023 I'm assigning it to this variable. Now from this variable I'm shifting it left side by 6 times. Why I am shifting it left side by 6 times? Because now I want, so 1023 I've given this entire thing 1023 to be in the position 6th bit till 15th bit. To have it exactly at this position, now how many bits I got to shift left? So 0 to 5. That means 0, 1, 2, 3, 4, 5. 6 bits I got to shift. Shift to the right. Right shift 6 bits, the value, then you will have your 1023. So positioned at this position from 6th bit till 15th bit. Next what you do, now, and that value is returned to DACR. Now DACR gets the value 1023 in the 6th to 15th bit. So and then this is what? So this is the 1023. This is 0 and this is 1023 value. This is the maximum. What you are saying is 1023, and this you'll repeat for how many times? How many times? 1023 times. See, it's the same thing. You get it. It's repeated for how many times? 1023. As long as the microcontroller loops here for 1023 times, so those many times it will remain in this I value 1023. And after that, now I need to get it down to the 0. Now I'll assign value is equal to 0. Now I'll write 0 here. To write 0 here, what is that I have to do? I have to make all the bit from 6th bit till 15th bits as 0, 0, 0, 0. Now when I make it, that is 0. The value 0 is assigned, and again value should be left shifted by 6 bits again. Now here also we left shifted it by 6 bits in order to take the data to 6th bit to 15th bit position of the DACR. Similarly we are doing here. Now what will happen? It will start plotting this. Now plotting this for how many times? Again 1023. After this, and again in an infinite loop, I will call the same function, this function again. Now it will start from 0 to 1023 times. It will start plotting this value, that is 1023. Now instead of the 1023, if I give half of it, say 512, so you'll not get the waveform till this point. You'll get half of it, and then it will continue. Now I'm giving the maximum. So because the maximum what I can give using the 10 bit as 1023, maximum I'm giving and the minimum I'm taking. So this is the maximum and this is the minimum, and like this it is repeated. I hope you understood this. This is to generate the square wave. Now what is that I want to do in order to generate a triangular wave? So this was easy. You understood how to generate the square wave. Now to understand how to generate a triangular wave, again the same thing. First I assign value 0 to 1022. To the value field I'll assign the 0 to 1022 in DACR in steps of 1 for 1023 times. I have the for loop here. Count is equal to 0, count less than 1023, count plus plus. And here in the previous experiment I had value is equal to 1023 permanently assigned. Now instead of value I'm taking the count itself, this count. Now count is what? 0 in the first iteration, 0 left shifted by 6 times. Now that means I'm taking that 0 to what position? This position. Now that is 0. It will start from here. This is 0. Voltage level 0. Next in the second iteration count will become 1. So 1 left shifted by 6. Now that 1 goes to the position 6th bit till 15th bit in the value field of DACR register. Next one is this, and this is with respect to the time. Now after the first iteration, for the second iteration to happen, it will take some finite amount of time. So it is shifting. This x-axis is time. This x-axis is time, and the y-axis is voltage. The first plot 0, it is plotted here, and you can, so from here to here, how many points you have? 1023 points here. 1023 points plotted here. So first point at the 0, and next point at 1, and why it is coming this side, why it is not going vertically upward, because this is with respect to the time. When you plot first point here, in the first iteration, and before plotting the second point in the second iteration, what will happen? The time will move and it comes here like this. So this is 0 and this is 1023. So many 1023 points you have written here. So this, and similarly in the next loop what I'm doing, so value is equal to 1023. I'm down counting 1023 because my waveform should go like this. Now it should decrease at this point. The value is 1023. Now I should decrement. Now 1023, count greater than 0, count minus minus. That is what I'm doing. First initial value is 1023, left shifted by 6 times. I take 1023 to the position 6th bit to 15th bit, and then assign it to DAC. This point is plotted again, and next in the next iteration count is decremented. It becomes 1022. So it's somewhere here. So the next point, next 1021, next 1020, 1019, 1018, it comes, and finally what comes here, it has reached 0. And again these two loops are repeated in a while loop, so you get continuous waveforms. So this is how to generate the triangular waveform. I hope you people understood how to generate the square wave and how to generate the triangular wave. Observe here. Now we are not discussing yet the external DAC interfacing. What we are discussing, how to convert the digital data into analog data using internal DAC, the DAC which is found inside the LPC2148. Now I hope you understood here. So for all 1023 times, what is the value we are supplying? 1023. That is the reason it remains here only. Now in the next loop, now we all of a sudden we are bringing it down to what? 0, and we continue here in this state for 1023 times. But here what we are doing in the triangular waveform, we are increasing it. We are starting from 0, and every iteration we increment the count till it reaches 1023, and from here in the next for loop we start from 1023 and start decreasing until it reaches 0. So this is how the square and the triangular waves are generated. So this is the program, square wave program using internal DAC. So this is the program. First we'll understand this program, square wave. Most of the things you have already understood, only everything is combined in the form of a program right now. Now one second. This one I think I'll just pull it. This is the comment line. The next one is save, and now so square wave program using internal DAC. Now LPC2148, this is the header file which you have to include, because even in the other programs also you understood. I have a global variable with the name count, and here now I have one more local variable inside the main with the name value, initialized to 0, count is also initialized to 0. And then the first thing that I need to do in the steps I showed you, the programming the internal DAC, first thing what you need to do is you need to make P0.25 act as analog output pin. How to make P0.25 act as analog output pin? So by using pin cell 1 register, because 0.25 is in the range 0.16 to 0.31, you have to make use of the pin cell 1 register, and this is the data. Now because when you give this data, it will make bit 18 and bit 19 of pin cell 1 as 10, and this 10 is the data which will make this P0.25 to operate as analog output. So we have made use, by writing this statement, we have made P0.25 to act as analog output. Next what? Now while 1, because I want the loops to be repeated continuously forever, while 1, and for count is equal to 0. This is what we are writing here. This is what we are writing, this for loop which I already explained you. Now one second again, this I'll comment line, I'll write this side. Save. Now here count is equal to 0, because initially it was initialized to count is equal to 0, count less than 1023, count plus plus. Now value is equal to 1023, DACR value, this value left shifted by 6. I hope you understood why you're doing left shift by 6, because I got to take this 1023 to the 6th bit to 15th bit position of DACR register. That is that, and then assign it to DACR. So assign it to DACR. Now this will start plotting a point here, somewhere here. Now just observe the mouse, somewhere here, and this is repeated for how many times? 1023 times. It will start plotting the points at the same level. So 1 point here, next point here, next point here, next point here, like this 1 0 2 3. And after that 1 0 2 3 times it will come out of the for loop, and next again count is equal to 0, count less than 1 0 2 3, count plus plus. Now what we are doing here, 1 second, I think this is for the square. I think I skipped one slide. Okay, count is equal to 0, count less than 1 0 2 3, count plus plus. Now what we are doing, value is equal to 0 and value left shifted by 6 and assign it to DACR. Now earlier the line was here at the peak. Now when it enters into the second for loop, the line all the way from the peak, it goes down and it start plotting the points for how many times, 0 to 1 0 2 3 times at the same level, because every time the value is same level it will go, and this is the closing for this for loop, and this is the closing for the while loop. Now it comes here again and starts repeating, displaying. Okay, now I have the execution and simulation in Keel and Protest. Now we'll execute this program and simulate it in the Keel, and later we'll go for simulating it in the Protest. Now and this is not a lab program again, this is a lab program, and even the lab program is based on using the external DAC. But if you understand this, that you can easily understand. Let me simulate this first. Now I'll copy the same program. So copy, and I have the Keel already open here. So I'll just say project, new microvision project. So I'll save it on the desktop. So new folder, let me call it as internal DAC. Since we are doing the square program,